Right then, plundering and pillaging password and passphrase planes for profit. I had to say that 10 times very slowly when I was thinking about naming it. The boring token stuff, I'm Will, Stealthploit Online, co-founded a UK-based pen testing company called In.security. Started off in forensics, defected to the dark side of pen testing in 2014, never looked back. Been very lucky and humbled to have trained and spoken in some cool places. Now I can finally add a security fest to that list too. I also help run DEFCON Password Village in Vegas, which is great, and yeah, that's me. Right, we're going to go for a whirlwind tour today. Do lots of different things, actually. I'm not going to speak through these, you can have a look, but it gives you kind of a taste of what we're going to be looking at. A lot of the attack-based stuff we're going to be looking at is things you'd want to look to do when your traditional word list and rule attack fails. Then we're going to look into some optimizations, some really weird and sometimes stupid things people have done in data breaches. And then we're going to show you a little tool that might help you automate some of your non-distributed workflows when you don't have hash top lists and servers everywhere, and you want to go to bed and you want to make sure that your whole night is spent cracking and that your computer is not just going to finish an attack and stop where it is. So let's start with passphrases. This is as simple as it gets. Hashcat, attack mode 1 combinator, give it 2 word lists, fire and forget. Now, you're going to see hashcat following us around on the slides. That's kind of a hint that I'm a bit of a hashcat fanboy. I appreciate there's more tools out there. And actually, we will be looking at another tool also. But most of these attacks predominantly focus on hashcat. Let's start adding delimiters. So a space, very common delimiter. Again, this is one of a few ways to do it, but as simple as it gets. Still combinator mode, take your 2 word lists, and we have -J and K available to us, which is make a single rule operation to the right or to the left word list. In this case, $space is a pender space in between the 2 word lists. You can see where we're going. Why not put some rules on top of that too? So we can still take our -J rule to insert our delimiter, but then we can pipe that to hashcat, run rules as normal. One rule to rule them still is something that I revamped in 2023. The original rule, one rule to rule them all, I did in 2017. It's a more efficient and optimized rule set, so it's fewer rules, but with roughly the same performance. So hopefully it should finish quicker when you're attacking your fast hashes. But we don't want to just stop at 2 elements. Of course we don't. We want to go to 3 and 4 and above and beyond. So there's many ways we can do this also. Print's processor is one very, very good option. It takes a single word list as input and then generates multiple elements. You do have a fair degree of control over what you can do with this. But here's an example where we want to take a word list and look for any password candidates with a minimum of 3 and a maximum of 4 elements from a top 100 list in this case. Pipe that to hashcat, and you can see the kind of output that you would get. Most of the screenshots here have either been taken from various data breaches or from pwned passwords, just so we've got some data sets to work from. We can again do delimited lists, so we can bolt on our -J again, but this time we're doing something a little bit different. In this one, we'd be feeding Print a pre-delimited word list. So you generate your word list, append a space to every entry, and then the -J bracket truncates the final character. So we could look at deleting the final space so there's no trailing space at the end. There are other tools to do this as well, and hashcat utils comes with combinator X, some people may or may not be aware of, and it can do a similar thing to prints, but there are some pros and cons depending on what you're looking at doing. On the right there, you can see at a high level what combinator X can kind of do, and you can chain up to 8 word lists with this, which is quite nice, and you can have custom separators. So if you don't want a space delimiter in between each one, you might just want, for example, a space there and then a colon in that one, or a comma, or whatever you want. So it does give you a greater degree of flexibility. You'd have to work with sort of more pre-processed lists if you were doing that with prints. But it is very useful, and it's another option. Like I said, it doesn't have the maximum 16-character length password limit the prints processor does. There's always multiple ways to do things. So there's the combinator X command. You take your 2, 3, 4 lists with your custom separators, which are of course optional, pipe that to hashcat, and then business as usual. But you'll notice all these passwords are lowercase, and people, society, humans, us, we like to do case toggling, especially with space delimited passphrases, because we like to capitalize the first letter of our words. So something like the 3 and E rules are really, really nice for this. A lot of good work's been done by Yanis, one of the guys on the hashcat team, who's got the toxic 3 rule. It comes with hashcat by default. And you can see here we've got some examples of what 3 and E can do, where you can case toggle the first letter after specific delimiters, either on custom separators or, well, your choice is your choice, really, whatever you want to do. And you can use this and nest it with itself and do things like, can't crack this, capitalize the first letter of every element in your chain. It's very, very easy to do it this way, assuming, of course, that people are capitalizing the first letters in their elements. And trust me, they are. I've seen it. So when you put all this together, you can then tack on something like toxic 3 rule onto the end of your combinator or your prints attack chain and get some kind of varied case toggling in your delimited passphrases. Okay, n-grams. These are really under-talked about and underused, but they're fantastic. You can do some n-gram analysis on your pot file with all your cracks that you've got. You can do it on word lists. You can do it on big texts, song lyrics, film scripts. Fantastic things when you're doing targeted word lists. And as you can see here, we've got an example. Security Fest is an awesome con, so you can see that in 2 and 3 gram form there. You can also do this for characters and character sets. So character n-grams are referred to generally as k-grams, where you can splice characters in a sort of rolling fashion. And character sets, so when you've got like password in uppercase, then QWERTY in lowercase, it can distinguish on that also and break them down into individual grams. There are 2 tools here that help assist in doing this, but I'd probably recommend Gramify, the latter one. It's much more modern, it's very fast, it's very efficient. And here's an example of a quick check I did running the Bible and the Quran against the pwn passwords list. So nothing kind of edited here, these were just raw stats. There are potentially a few more numbers now, as I ran these tests a month or 2 ago. But you can see when you're looking at 2 through 6 n-grams in both sort of English language and native Quran and the English version of the Quran, the types of passwords that are coming out. And in the bottom case, for native text, we can then, of course, convert that to Arabic or whatever language you're working in. Okay, rules root, combi rules profit. That's the best way I could get this into a slide. Nice little attack, probably not used as much as it should. You've done a fast run at an AD dump, a data breach, whatever you're going at. So you've probably done RockQ, everyone loves RockQ, and you've used a rule set, and now you've got a load of founds in your pot file. What you want to then do is take those founds, mangle them. In this case, I'm attacking the Gamigo data breach, which I think was about 2016. And I've got a word list here, Gamigo, which has already got 1 rule to rule them still, and these are just the output of that file, effectively, those candidates. We then want to create alpha and non-alpha word lists from that, and then run those in combinator mode. And you'd be amazed at how those combinations, when all bolted together, can generate new passwords that you otherwise wouldn't have had. Okay, scaling masks. Just one slide on this, because it took me ages to figure out how to do this, and I was asking people for help, and then it was like, okay, this kind of makes sense, hopefully. Bit of an edge case. What if you know something about the password? Like you know the start and the end, but you have no idea about the middle. I was scratching my head because I was trying to do this in different ways, and I couldn't figure out how to do it without a significant amount of list pre-processing. And then, as a raw example, let's say you know it starts with a letter, a number, ends with a special character, and let's say we have lower alpha in the middle. What you want to do is you want to take your first character in attack mode 6, so A6 is hybrid, word list plus mask. So you could put all of your numbers in a word list file. You can then apply your mask, in this case lowercase characters, -I to increment it, so you start at 2 and of course build up. Pipe that to hashcat and then add your final special character as a rule, so it'll tack that onto the end of each one. You get the exact same effect doing it in A3 mode. You can see in this case though, we're starting at an increment position of 2 after that first decimal and building up, again tacking on your special character at the end. Now, there will be a difference in this, because in attack mode 6, you're working with a 32-bit integer for your buffer, whereas in attack mode 3, you've got a 64-bit. So the amount of L's or A's, if you're attacking a full printable ASCII character set, will greatly depend on the attack mode you use. You can't just add on 10, 12 A's Firstly, it won't finish in your lifetime. B, it's not a very efficient way to do it. But there will be limits, and for this, it's a matter of trial and error to see how far you can get before you get what's called an integer overflow, where you've just run out of numbers. Okay, targeted Markov chains. So Markov modeling is the process of identifying the statistic probability of a character based on the previous character and its placement in the password. For example, if something starts with the letter Q, there's a high chance the next letter might be U. Now, hashcat has an internal Markov table, and it's built off RockQ, which was, of course, a data breach back in 2007 or 8. And that's fine, that's great. Everyone who's ever done password cracking has probably heard of RockQ. It's been that kind of thing that stood up till the test of time. However, what if you're attacking something very, very targeted? For example, the Lifeboat community, which was a Minecraft-related forum, I believe, was popped quite a while ago. And let's say you've got a Minecraft-related breach that you've got and you want to start cracking passwords. It's reasonable to say that a Minecraft breach, there may be many Minecraft-related passwords, reasonable to assume. So what I did was I went online, downloaded as many things from Minecraft wikis that I could find that I'm not a Minecraft player, probably an unpopular statement, all the objects, skins, names, you name it, compiled a massive list, ran one rule over the top of that to generate a base word list of what I thought were mangled Minecraft passwords. You then need to convert that into a Markov model using hestat2gen. It comes with hashcat utils. You then need to compress it into a format that hashcat wants to accept. And then I finally ran that attack, but rather than using hashcat's default inbuilt Markov model of RockQ, I apply my own 8-character brute force. We're talking about brute forcing here, okay? Not dictionary attacks. And after 60 minutes of runtime, I found that using my Minecraft model, I recovered over 10,000 more passwords in that first hour than I would have done when I retested it using the inbuilt RockQ Markov. Now, ultimately, when you're talking about brute forcing, if you've actually got the time to exhaust that attack, you're always going to end up with the same number. This is all about getting as many cracks as you can in the shortest possible time to increase your chances. That's what Markov's all about. But again, if you've got targeted breaches, it's something to look at. The next step in our journey, cracking hashes with hashes, blew my mind when I first heard about this. So, let's say you are looking to upgrade the security of your users and your application. You're currently using MD5 or something else. You want to go to bcrypt, a very common one, a very solid, very cracking-resistant algorithm. Okay, what do? Do you set the passwords for all your users and annoy a lot of people? Do you get it to update the hash to bcrypt on next login? Do you rehash the hash? You've got some options available to you, some of which require you to store both the original hash and the bcrypt in the database. Now, to understand what password or hash shucking is, and we're going to build up to that in the next slide, we need to understand how this works. And hashcat has a mode, in this case, for looking for nested internal hash. As you can see here, we've just taken an MD5 of In.security, run that through bcrypt, and you can see we've got a mode here for attacking bcrypt of MD5 of pass. So we can attack that, and that's fine. But Sam Crowley, who goes by Chicken Man, one of the core hashcat developers, did a fantastic talk in DEFCON Password Village a few years back called What the Shuck? And it illustrates actually how this is quite a bad thing, using an unsalted hash and then layering bcrypt over the top of it, for example. And this is why. Let's say you're a user, a very happy user, because you've got an awesome password. And that's not uncrackable. 12 characters, lower ASCII, numeric. Hard, not impossible to crack. You've used that password on 2 sites. Fine. One site uses SHA-256. The other site uses bcrypt of SHA-256. Those sites get popped. Now an attacker has got 2 data breaches. Okay, fine. Now, if they can match up the email addresses of the 2 users, and let's say they've cracked the SHA-256, fine. They might try and reuse that password. Okay, fair enough. But let's say they don't know. What they can do is take uncracked SHA-256 lists, and they can then run bcrypt over that to see if they can get a match. If they can generate the resulting bcrypt from the inner unsalted SHA-256, they now know that whilst they don't have the clear text password, they now have the SHA-256 that was originally used. So when they go to crack that, they're now not cracking in bcrypt land, they're now cracking in SHA-256 land, which is, of course, substantially faster. So if the inner hash is a fast hash and it needs to be unsalted, if the inner hash is salted, this wouldn't work, then the outer hash, in this case the bcrypt, can be shucked, and you can be attacking a SHA-256 instead. In a pen test environment, because I'm a pen tester by day job, you could be looking to do this with NTLMs, for example. In Windows, everything under hood's an NT hash, Kerberos, cache creds. And hashcat for a long time has had the ability for you to take uncracked NT hashes and throw them against your NTLM v2s that you might have caught from Responder or somewhere else. Again, if you are able to crack a hash, you don't have the clear text password, but in an AD environment, you can now pass the hash, business as usual. Okay, now getting to some really fun stuff. Unicode, multi-byte characters. Anyone here cracked foreign language stuff before? Cracking emojis? A few oohs, a few yeah, maybe. It's great fun. People do use emojis as one example. Of course, we've got so many languages, so many ways of writing characters, lots of things that fall outside our typical ASCII range. And UTF-8 uses between 1 and 4 bytes, so it gets a bit complex. Now, in this example, we can actually see on the right here, we're looking at the code points of 600 to 6FF, which is Arabic, which is this middle section here, okay? We've got, of course, code points for emojicons and every other type of language you can imagine. UTF-8 is a very, very big, expansive set of characters. So what we can do is we've got a couple of options. Now, occasionally you can actually write these native Unicode characters directly via standard into hashcat, but hashcat processes bytes, not characters. And the preferred method and the advised method is always to use hex at the bottom. So for example, in this previous slide, you can see at the bottom here, we've got some Arabic numbers that use UTF-8, D8, 80, D8, 81. What you do is you build a custom character set that includes the hex characters of every permutation from that UTF-8 table. You then run that together, passing hex char sets, so hashcat knows it's interpreting hex, and then you apply your mask. In this case, we're looking at like an emoji attack. And you can see we've created 4 custom character sets, and we've got question mark 1, 2, 3, 4 times. So in this instance, 1, 2, 3, 4 accounts for a single emoji, not 12 emojis, because emojis use 4 UTF-8 hex bytes. Use them in rules. Why not? Hashcat support hex and rules. As you can see at the top, we need to do a bit of formatting. We need to escape them. So you can append, prepend, you can do both, you can have some fun, and people really do use these in passwords, okay? These are real passwords, especially when people are, of course, creating accounts on mobile devices these days. Emojis are becoming very prevalent. Look through all your word lists, all your founds, all your cracks, everything you've ever got, and start looking for those non-ASCII characters to build UTF-8, to build Unicode word lists that you can then use. You could script out, you've got all the code points there, and you can see what we've got, tons and tons of text files containing various UTF-8 characters. Then you can run that against your data breaches, run that against your password lists. And this is all stuff that's, again, data breach material, but it's crazy stuff that I would never crack in a million years using a simple rock queue and one rule attack or best 64, whatever it is you're using. So you can get all sorts of stuff that comes out of these password attacks, and you wouldn't be knowing about it unless you're trying to include Unicode in that, especially, of course, if you are assessing or doing testing in other countries where people will be using different keyboard layouts and other things. So, on the topic of keyboard layouts, transliteration, that looks like a pretty good password, right? No one's going to say yes, because I'm going to put you on the spot. Of course you're not. But generally, to the human eye, societally speaking, that looks like a pretty good password. It doesn't look like it's based off a dictionary. But what if I were to tell you that that password was caught in 890 data breaches in Have I Been Pwned? And it's probably more than that now. Okay, we've just taken the NT hash of that. Okay, and that's because those actual characters are transliterated when my space password is typed into a Zhuyin keyboard layout, which is very, very prevalent in Taiwan, for example. Now, the transliterated password might be hashed. I'm not going to stand here and say it will always be hashed. It will very much depend on the system, the keyboard, how that's being passed to the operating system, granted. But it creates some really weird and wonderful things, because to the human eye, that looks like a face-rolled password-generated password. And it really, really isn't. So you can look at doing further work on this, and you can see the amount of occurrences, in this case it is Have I Been Pwned, where those transliterated passwords have been hashed, not the native Unicode character. Okay, and you can see Russian Cyrillic is quite a popular one there, and we've got some other examples. A lot of Polish people don't seem to know their passwords. I don't know why that is. Now, These were called table lookup attacks that you could do in hashcat legacy, okay? It was attack mode 5. But there is now a very good model alternative. So if you are looking at doing these types of attacks, you can build up your lookup tables and use them to transliterate to whatever your sort of target country or language or character set of choice is. And again, depending on the data set you're analyzing, you'd be amazed at some of the results you can get. So you take your base words. I downloaded a list of Russian words. It was just a Russian word list from GitHub. Fine. Made my lookup table. Performed the translit. Fine, good. You'll notice there are some Russian characters in there as well. For cleanliness, I wanted to get rid of them and just use whatever I found in there was ASCII. Sometimes if you've got a bit of a dirty base word list, if it's not quite cleaned, you can get some character maps that don't quite work. But then, throw your new transliterated password against a data breach, and oh my God, it cracked. I couldn't believe how many cracks I got from that. And then just for fun, if you want, reverse the translit lookup and then translate back. So we can see that top entry is Alexandrovich, written on a Russian keyboard layout. And that's, of course, just for fun. But those are real cracks and real databases. And who's going to have those in their word lists? No one. So all of this is building up to entropy, because you hear it thrown around a lot, and entropy is valid, and it's great, and it's fine, but only for machine-generated passwords. Entropy does not apply to human-generated passwords, because for the passwords we choose, it only societally quantifies how they look. Just like that top password, you look at it and you think it's random, but actually that's a terrible password, okay? Unless it's a password manager-generated password, or another way that's known to be secure, entropy doesn't apply, okay? So the key space of that is, sorry, not the key space, the entropy of that is 62 bits. That's not terrible. It doesn't quite reach what we should be aiming for to minimum these days, but that is not terrible. But it's a terrible password, okay? And it's a terrible password because no one does these unintelligent brute force attacks, which is what entropy really models against. No one uses Markov disable. Okay, Markov is always there working in the background for us. Rule optimizations. Okay, so this is going a little bit deeper in terms of optimizing out no operations in your rules. Now, the maximum password length you've got when attacking fast hashes in a wordless mode, mode A0, is 31. Now, there will be many, many rules in the rule sets you use that actually generate candidates that go beyond that. And this is, of course, assuming you're using -O, which is optimized kernels. You can attack passwords up to 255, 256 characters. But using -O, which everyone uses because the speed increases are fantastic, you are limited to 31. Now, D is duplicate, and P rule is append the duplicated word a number of times. And you can see where we're going here. So if we take the word password, we can duplicate it once or twice. Of course, the third line there will, of course, be 24 characters there for password, password, password. But when we try and do it a third time, that's a no operation. It gets us above 31 character limit. That would be 32. So that operation is ruled out, and we're back to square one. Similarly, with the D rule at the bottom, we can duplicate our word, in.sec. We can append 1, 2, 3 to it. We can duplicate, append 1, 2, 3, but then when we duplicate again, it will duplicate the entire current buffer, not the original root base word. So you can see how that's built up there. If we add a last exclamation mark on the end, that puts us into 32 characters, no operation, we don't get it. Then there are situations where the final length of your password candidate is less than the intermediate length of your password candidate. And if we're assuming we're talking about attacking passwords that are 8 characters or above, because for fast hashes you can really trivially nowadays brute force the entire key space of up to 8, you can get into situations where, for example, stepping through it again, take the password of super secure 1, prepend 1, 2, 3 to it, fine. Then do a P4. We're not going to fit 4 times that length in. It's going to exceed 31. But then we add a -9, which is truncated to the 9th character. So now our final candidate is within 31 limits, and that P4 becomes redundant. Optimize it out. That's a single cycle of compute you're wasting, which is going to be never noticeable for a single entry, but built up over time, there are going to be plenty of rules that actually produce redundant no operations, assuming you're attacking passwords of length 8 or higher. Again, a couple of tools that could help you, and rule processor is definitely my favorite. Okay, let's jump into the rabbit hole further. Nested hashing. Now, I don't have answers for most of these data breaches coming up because it's anyone's guess. Sometimes systems will store iterative hashes natively. Example, SHA-1 of a SHA-1 of a pass. Fine. But sometimes you'll find that hashes find their way into passwords, and you have no idea why. Sometimes it might be because of an insecure password generator that the user uses, and it's transparent to them. Sometimes it's just complete stupidity. And most of the time, I have no idea. So I have no answers for most of these. These next few slides are data breaches I've taken from HashMob, which is a pretty good site to look at for this kind of stuff. And you'll see in the first example, we have a breach, 27.8 million. These are all MD5 breaches, by the way, single vanilla MD5s. 5 instances of a nested MD5. Meh, OK. Let's say 5 people were trying to be clever and they pasted in an MD5 as their password. 5 isn't too much, we can live with that. 40 MD5s of MD5s. And this tool I'm using at the bottom is MDX-find, and you can hopefully see that we're illustrating where the nested hashes lie. So for example, at the top here, we've got L04, which cracks to the hash F5, but we look down here, we've got the first iteration, and then we've got the second iteration beneath it. So we're showing you where the nesting happens each time. Up to 40 on that one. If we go to Yoku, which was a massive data breach, 48 million records, 692 nested MD5s. But what do we notice about this one? The plain texts are hashes. Can't tell you how they got there. Maybe a polluted data set before it was passed across. Who knows? The only way they should really be in there is if those hashes were in a word list. And I'm fairly confident that hashes wouldn't be in a word list that would crack, of course. But who knows? But I did look at them and think they look a bit suspicious, so let's just try and crack them anyway. And sure enough, the actual passwords were beneath it. So don't know how they got there. Sometimes you do see these nuances in data breaches. And in the same breach, inception, MD5 of MD5 of MD5 of password. I'm out of options at this stage. Needless to say, though, we've got the plain text on the right. So you do see these things every now and again. So when you are attacking, if you are attacking data breaches for research, and you've done all of your usual attacks, try nesting just to see. You might be surprised. You might get some extra low-hanging fruit. Intermediate case sensitivity. Let's take the word password. Fine. We're going to hash it. Now, hashcat defaults to using lowercase, and that's fine, and many people do. But let's say you then nest the final hash as an uppercase as well. So you can see now we've got the lower and the uppercase of the intermediate hash. Now, the final hash is, of course, going to be very, very different because we've hashed completely different characters. But if we actually take these, what I've got here is the top 20 passwords from RockU. I've then got on the left column the lowercase final hash, the uppercase final hash. And actually from here, you can see the password starting 353 is the 4th one down on the right there, lines up to password. And as you go through, you'll see that actually we've got hashes that have appeared in pwned passwords that reside from the lower and the uppercase passwords. Hashcat loves jumping around on this slide. Okay, so lots going on there, and of course the number of times they've appeared in these respective data breaches. So might be something else to look into, making sure that if you are looking at nesting hashes, you're considering case-sensitive lowercase and uppercase intermediate hashes. Now, password placebos. Okay, one example here from Chicken Man. You know what you shouldn't be using? Bitcoin addresses as your password. Yeah, oh, I love this when I found it. I looked at his tweet and I was like, okay, I'm going to have to try this. Yes, fantastic. So I did a run, 172 people, I'm not going to say idiots, but people have used their Bitcoin address as their password. Okay, there they are on the right, fantastic. And I thought, I can't stop there. That's an itch I've got to scratch. Let's go to Ethereum. So I downloaded the top 33 million richest Ethereum wallets, and surprise, surprise, they came down. But what's this? Not only have they taken their Ethereum wallet, they've even added 123 and put an exclamation mark at the end. All these things that we as humans do because we believe it makes our password stronger. So someone's gone to the effort. Luckily, I was using a base. I wrote a quick rule just to see 1, 1, 2, 1, 2, 3, the usual stuff. And I was quite surprised to see that really people had wanted to make sure, you know, my Ethereum wallet as a password isn't good enough, but a 1, 2, 3, that will keep me secure. Don't do it. Just don't do it. Okay, I then thought, okay, what's next? National identity numbers or very personal numbers. Now, caveat here, I'm not saying that these examples couldn't inadvertently be used as a password without it being an ID number. Yes, there might be a few here that slip through the cracks. But
When you look, and I really hope I've got Sweden right here. People look at me thinking, oh, Will's got it wrong. When you actually set up some masks and attacks to attack varying formats of identity numbers, again, you can see the number of cracks that we've got in pwn passwords. Don't do this, okay? For those passwords that were actually identity numbers, don't do this. Okay, another example. An insecure password generator. Well, this one was actually, I think, originating from a Stack Overflow. But you get people, when you look for how to generate secure passwords, and let's say you're not aware of password managers, the amount of things you see out there that people tell you to do are phenomenal. In this example, take the Unix epoch timestamp, SHA-256 it, and then base64 it, and then just use 32 characters of that resulting value. Chicken Man jumped in, hashcat guy, and said, this is actually a thing, what the hell is everyone doing? So I thought, I need to get on that bandwagon. I tried SHA-1 instead, and I only went back as far as 2015. Within 20 seconds, I got a hit, that 19D. Working it backwards, you can see where the truncation ends after the highlights, and that resolved back to a date when converting it back to a Unix timestamp. Don't do these things. Science. What's next? Where do we go? Downloaded a list of about 190,000 elements, chemical compound formulas. Let's throw it at some data breaches. Using prints, I set a minimum password of 10 just to make sure it's sufficiently long enough that people doing a bit of an 8-character face roll, I kind of got them out of the process. Ran that through, SHA-1. I let it run for 12 hours, and I got 121 cracks. Okay? Could some of these have been generated without, could these have been generated by non-scientists? Yes, absolutely, someone could have done it. However, some of the things I saw were absolutely fantastic, and I definitely think I should get a chemistry Nobel Prize for new compound discovery, because some of those look pretty awesome. Just don't do these things. Here's a good example, Stack Overflow. I love linguistics. My approach to create memorable passwords with a high level of entropy. No, sorry, entropy doesn't apply to passwords generated by you, a human. It's 57 bits, not the worst, but not great either. Maybe it's not susceptible to dictionary attacks, but it's definitely susceptible to trivial attacks. Don't do it. That, I just don't know how anyone could write that. Short passwords with a decent strength. They are literally opposite. Short is not a decent strength. So I did it, sure enough. Yes, all the passwords came flying down, starting with a capital consonant and then alternating vowel consonant for 10 characters. I also found it very interesting that the optional parameter was to add a digit. It wasn't add a digit, it was an optional parameter to add a digit. But either way, alternate consonants and vowels, don't do it. Okay, that brings up to the last part, automating non-distributed hashcat workflows. So, about half an hour before the talk, I made this repository public, so it's now available. This is simply a wrapper, a hashcat wrapper, nothing more, okay? Now, there's a Windows bash script variant, and there's a Linux bash script variant. I deliberately did a Windows bash script. This was going to be painful to do in PowerShell. And when I run hashcat from Windows, I use CMD. So this is why I've done it. And what this is supposed to do is just to help minimize downtime. Those times where I'm cracking passwords and I've got to go to bed and I don't want to leave my computer on. Or let's say I want to go to bed and I leave my computer on overnight, but I know the attack that I'm running is going to finish in an hour. And then there's another 7 hours of wasted time. What this can do is it will go through any of those attacks that we've got there and chain them together so that when one stops, the next one starts. It's got lots of variations of different ones. It logs everything it does. And what you do is select 16, custom attack chain, select the options you want, and then leave it possibly forever, depending on the rules and the word lists you give it. This is what you need to set in the respective Windows or Linux script. Give it a path to your pot file, a folder for your word lists, a folder for your rules, a folder for nested rules if you want to keep them separate. Basically, all you do is just go through and add in your respective file paths. I've also included the rlite binary from Sinosure Prime because it's fantastic for in-place sorting and deduplication. Windows is terrible. Windows sort does have an undocumented unique switch, but it starts to fail massively when you get outside of ASCII characters. And this is very, very quick, and it's very, very computationally efficient. So make sure that the rlight binary and your hash catalyst scripts are in the same folder, the hashcat folder. This is what the logging looks like. And what I'm going to try to do, and I wasn't planning on doing this, but what I'm going to try to do is hopefully lose my video because I was going to do a demo. Is that focused on a window rather than screen? The output died. I'll restart the presentation, and if anyone wants to see a demo after the talk, I will be happy to give it to them. Now you're back. OK, I was going to do a live demo. Find me after the talk. You can see what it's doing here, though. Attack logging. It will timestamp each attack you give it. And for attacks where you've got run every single rule in my folder against this word list, or run every single word list against all of these rules, it will individually timestamp each attack it does before continuing to the next. This is important, because if you've got a failing attack, maybe you've given it something that's an infeasible attack for hashcat to calculate. Maybe it overflows. Hash catalyst will just keep going. So if you've got a massive, massive word list and a massive rule set, and it should have taken 20 hours, but the timestamp showed it finished in 2 minutes, maybe assign to debug and go and have a look what went wrong. But I do want to stress, this is just to have some fun with. You can, of course, plug in your own attacks into the script to make them whatever you want to be, and hopefully that will help automate and certainly minimize some downtime of your hashcat workflows. We've got free training for anyone who's interested and wants to get their hands dirty. 4 hours, 15 videos spread over YouTube, starting at the very basics, going all the way into Unicode and passphrases and other stuff. There's a VM to download, pre-built with all the hands-on challenges, completely free. There's an old CTF that we released in 2018. That's still there, but the cryptocurrency price has definitely gone, so you can get your hands dirty there. And for anyone who really, really wants to go at this, here's a challenge hash for you. And if you can crack this and find me during a Security Fest, you can win a fabled, priceless, invaluable In.security challenge coin. I've got a spare hacking one, so if anyone gets it, fantastic. Find me, tweet me, whatever, and we'll get that across to you. Now, you're all thinking, that's going to be pretty hard. It is, or may, use some of the techniques that we've discussed in this talk. So don't just think a simple word list attack will beat this. But hey, if you want to have some fun, please do. But that's it. Hopefully you've enjoyed that. Thanks so much for listening. And we've probably got maybe time for questions before your second coffee break.
Perfect. Thank you so much for a really good talk. Really interesting. Not my forte whatsoever, but it's really cool. Questions? Surely there are a lot of questions. Come on, do it. Questions? Raise your hand. Like one question. Come on. Yeah, we got one.
Is it on? Yes. Let's assume I am using the password script kitty as one word, and you have it in your dictionary as well. Obviously, you can crack it, right? If I swap the middle I for a 1, can you explain the rule in hashcat that would target that specific password?
Yeah, it would be a substitution rule. So on the hashcat wiki, there's a nice table of all the rules. So you've got things like insert and overwrite. Now, for that explicit use case, I would need to know, of course, the position of I in there to target that I. And it would be the lowercase s for substitute, then the lowercase I, then a 1. So when it sees an I, change to a 1 in this case. Now, that would be actually an SI1 would be for any place in the password. If you wanted a specific positional requirement, I would need to target it differently. But the rule SI1 should do that.
So SI1,
yeah.
It will swap the middle.
Well, that's a position-independent rule. So if the I was in the second position or the 5th or the 10th, that rule should just look for the lowercase I and swap it to a 1 regardless of where it is.
Yeah, but I have multiple I's and I only want to swap 1.
Oh, you only want to swap 1?
Yeah.
Okay, that would be a positional.
I only swapped 1 of the I's in my password.
Yeah.
Can you create a rule that targets that?
I could create a rule, but I don't know the rule modifier to do it off the top of my head. I could do it and probably do it for you after the talk, though. Yeah.
Okay, thank you. We can. Yeah.
No problem.
Questions? Come on. Be brave. No one?
No one wants to tell me their password. What?
You can have mine. No,
It's
no
all right.
questions? Yeah, we have one more.
Security Fest 123 exclamation mark was cracked long ago.
Oh,
don't
you
worry.
already know it. God damn it.
So we were talking a lot about password, how send safe and all that stuff. Is there anything you would hide? Oh, might have stayed up as well.
Right.
Would there anything you would recommend to provide for a good password for a user?
Anything that's generated by a password manager. Anything that's generated without a human brain. So, yeah, I mean, there are some password manager generated passwords is absolutely the answer, granted. But if we're going to go to absolute specifics, based on modern entropy requirements for what is considered to be uncrackable passwords, assuming you are using upper, lower, alpha, and numeric, you need 13 characters for that password to be uncrackable. Okay? 14 if you drop the special characters and just use mixed alphanumeric. Now, I only say this because, and I was a victim of this too, for many years, my password manager, I used to move it to like 100 characters and generate these massive things. But there's no point, you're not really gaining actually any security benefit from that because it doesn't matter. All that happens is you do that, and then one day you realize you've done it for like your TV, or you need to input something in a remote, and you curse yourself. Or in my case, go and change my password to like a 13-character password-generated string.
Sounds good.
Yeah.
So should we still be aware of like LLMs or AIs right now? Should we ask them to ask
Oh,
a password,
so
or does it become a problem?
I'm not an AI LLM guy, but for everything I've seen and the hallucinations I've seen, the blanket advice is don't. Just don't use it. That might be an unpopular opinion, but I can only base on my experiences and opinions, and I would say avoid it like the plague for this kind of stuff. Yeah,
All right. Thank you very much.
no problem.
Anyone else? Yep, we have. Now we're warming up. I like this. Good. Sorry, Will.
All good.
Thank you for the presentation. So I know for a fact that in programming languages there exist, secure random number generators and non-secure random number generators. Can you crack passwords that are made from non-secure random number generators?
The answer is possibly, but if I have, I would have done it unknowingly. If you're actually using a CSPRNG, a properly cryptographic secure random number generator, then I should not be able to do so, no. And I almost certainly haven't. But I can't give you explicit use cases, because if I have cracked insecure password-generated passwords, I wouldn't have probably known. I've never targeted specifically what I believe to be a non-secure password generator. That almost leads into that kind of Stack Overflow post and the truncation of hashes and that kind of stuff. Those would be potentially insecure password generators. But unless you're specifically targeting it, if I have, I wouldn't have known about it. The answer is probably, though. Because if they're insecure, then by virtue, they're not secure. Yeah.
Thank you.
No problem.
One last one? Or anyone? Okay. Well, thank you, Will, for an excellent talk.
Thank you very much.